Hello, I'm Naoshi Kaneko from Aoyama Gakuin University. This video explains our entry to the GENEA challenge entitled TransGesture Autoregressive Gesture Generation with RNN-Transducer. Co-speech gesture generation is the task of generating gestures represented as body motion from the given speech input. The task is a sequence-to-sequence problem where the input speech is translated into aligned body motion. So far, researchers have explored several input modalities, including audio, text, or speaker identities, and their combinations to generate more convincing gestures. From another perspective, a long-term trend in automatic gesture generation is adopting architectures of speech recognition and machine translation, such as deep speech, sec-to-sec, and transformers. From early work to recent studies, many gesture generation methods employ these architectures. This is a natural choice since input modalities of gesture generation are closely related to these tasks, namely speech audio or text transcriptions. These models are broadly categorized into encoder-based models, such as deep speech, and attention-based encoder-decoder models, such as attention sec-to-sec and transformers. However, these models have several specific pros and cons. Encoder-based models are simple and fast, but their frame-by-frame outputs are independent of each other. Attention-based encoder-decoder models can look at interdependent relationships while they require full input at once to compute attention. In this work, we pay attention to the third type of model, namely RNN-Transducers, which has attracted recent attention from the speech recognition field. An RNN-Transducer is composed of three networks, namely encoder, prediction network, and joint network. Encoder is similar to the ones used in encoder-based models. It takes input speech and maps them to latent representation. Prediction network is autoregressive. It takes the transducer's previous output and maps it to another latent representation, which is useful for predicting the next output. Finally, joint network takes the two latent representations from encoder and prediction network, joins them, and produces the current output. Thanks to this architecture, RNN transducers have several good properties for gesture generation, namely non-independent outputs and streamable processing. To the best of our knowledge, RNN transducers have not been adapted for gesture generation, despite these preferable properties. Based on RNN transducers, we designed our model named TransGesture. Audio encoder takes an audio feature at the current time and processes it through a set of a free connected layer, a two-layered gated recurrent unit, and a free connected layer, resulting in a later feature vector. Prediction network takes the previous output of joint network and produces another latent feature. We use the same architecture for prediction network and audio encoder. Joint network takes the two latent vectors, integrate them by element-wise summation, followed by a free connected layer, and outputs the motion of current time. We keep each network structure to be simple to see the potential of manual RNN transducers. Following the previous studies of audio-driven gesture generation methods, we choose multi-frequency substral coefficients (MSCC) as input audio features. Regarding output motion, we consider the upper body without fingers. The output motion representation is joint angles relative to a T-pose, which are parameterized using the exponential map. Each dimension of the joint angles is normalized by subtracting the mean and dividing by the absolute maximum over the training set, resulting in the range of -1 to 1. As a post-processing, we applied a Savitsky-Golay filter to the generated exponential maps. We trained our model only on the training split. We used all the samples in the training set and split each sample into chunks of 256 frames, approximately 8.53 seconds. For training, we use the standard MSE loss between the model outputs and ground truth motions. We also use MSE loss for motion velocity. However, by using these loss terms, we observe that our network outputs tend to collapse to the mean pose. Thus, to avoid such collapsing, we introduce new loss functions, namely statistical losses. The statistical losses ensure that the statistical characteristics of the generated and ground truth gestures are close. Specifically, our system uses the mean and variance of the gestures. The final loss function is the weighted sum of the 4 loss terms. Here, we show some example videos of the generated gestures.
So I felt like you're more being in like this static or like.
We always like whenever we go on vacation, I like to listen like books on tape. Like I am interested, like, would these books be like decent for car rides? Because I like no, they would be boring.
For crowdsourced subjective evaluation, we participated in the upper body category. The label indicating our challenge entry is USL. Here are the human likeness evaluation results. Our entry attained the lowest median score among the participating systems. And here are the appropriateness evaluation results. Our entry USL attained the largest gray bar, meaning highest tight response rate among all the entries. As we saw, our system was not so positively evaluated in subjective evaluations. There are several possible reasons. First, our generated gestures were unclear and had limited diversity in motion. The gestures mainly contained forearm movements with constant speed and barely produced the movements in the head, body, and upper arms. Second, we observed that some of our generated gestures were somewhat too symmetric. Both arms did similar movements with similar height and speed. Third, our entry did not contain finger movements, and fingers stayed in a bit unnatural positions. We propose a gesture generation model based on an RNN-Transducer. The model is composed of 3 simple networks. It is autoregressive and potentially streamable. Unfortunately, the quality of generated gestures was not satisfactory. Through the challenge, we had spent too much time implementing and debugging the prototype system. We especially suffered from collapsing to the mean pose. After the challenge submission, we noticed that several training chunks barely contained gesticulated frames. Since the challenge dataset is in a 2-person conversational setting, the dataset contains some amount of silence frames where the corresponding gesticulations are also stopped. Exploring a filtering strategy for such chunks would be helpful. That's it from me. Thank you for your attention.